let's start. Let me say a few words first. Good morning here in Taiwan, and of course, good evening, I think, or in America, in Pittsburgh, in Carnegie, Mellon. And we are very happy today. Actually very exciting to have Professor Zac Manchester on to give us the talk on the engineering the world's smallest spacecraft. I believe he will talk about his venture into the Starshot business and things like that. But then I would say that just to introduce him, Professor Manchester, he graduated, he got his PhD from Cornell, and then and already he was then working on on the chipset. I remember seeing news about him already when he was a PhD student for his venture, and then he later on he moved to after graduation he moved to I think to Harvard, right, for postdoc. Yep. And then he shipped to moved to Ames, NASA Ames, and I also saw news about his mission. I think this, we have about 50 or 100 chipset, right? Ejected from a spacecraft, mother spacecraft, and then only a few months ago, I found that he had moved to Carnegie Mellon, in the Robotic Institute. I think that's great. And we will listen to him now, and I hope that from him, this kind of very exciting possibility in future and very suitable for Taiwan, since Taiwan is a very small country, so the chipset is right for Taiwan. And hope that Professor Manchester would be happy to have some cooperation with us, to teach us if we have a student or researcher interested in this business. Okay, Zac, it's all yours now.
Okay, great. Thanks for the introduction. So I guess I'd like to start out with a question for the audience. That is a question I like to ask at the beginning of these talks when I talk about chipsets. And the question is, what if flying a satellite cost less than your smartphone? Typically, we think of spacecraft as these enormously expensive things to build and to launch, and typically the domain of national governments, militaries, and large corporations, this kind of thing, but not something that the average person can really sort of touch and be involved with, right? So I like to pose this question, and I think that if you really think about this idea, it goes quite deep and kind of not only in the sort of accessibility side for having more students and people in smaller countries involved in spaceflight, but also kind of the entire paradigm for how we design, build, and think about spacecraft changes. And I think there's a lot of opportunity for faster technology development and more risk-taking and less conservatism if we can build spacecraft that are smaller and cheaper. So I'd like to sort of start out with this question, and maybe everyone can kind of think about this as I talk a bit, and maybe at the end we can revisit the question, and maybe you'll have your own ideas. So a few things that I would do that this kind of comes to mind for me that I just want to throw out there as possibilities in this domain, and things that you might do if satellites were dramatically cheaper. So one of them is agriculture. It turns out that agriculture as an industry is the second largest consumer of satellite remote sensing data in the world after sort of national defense. And this data in the last, say, decade has become very widely used in developed countries. And it turns out you can get all kinds of information about crop health, moisture levels, nitrogen levels in the soil, all sorts of things from this kind of satellite imagery. And large agribusinesses in the US and Europe are buying this data and applying machine learning algorithms to it to target at the square meter level where they apply water and fertilizer to optimize crop yields and reduce costs and reduce water usage. But right now, this data and the sort of analytics that go along with it are too expensive to deploy in developing countries and poorer countries. And those are the places where it could potentially help the most. So one of the things I would think about doing if we had lower cost satellites is sort of getting more of this data and putting it in the hands of people who could use it. Another is somewhat obviously weather forecasting is another amazing use case for satellite data that touches all of our lives. Currently, though, we don't have enough of it. There's been a lot of news about how there's been less investment in the US in our satellite remote sensing capabilities for weather forecasting, and the spacecraft that we currently use for this are past their design life and need to be replaced. There's also a number of newer techniques for sort of probing the atmosphere and studying the climate and the weather that require that work by using GPS signals as they sort of glance through the atmosphere. And to use this sort of technique called GPS occultations, you really need a lot of data. You'd like to have a lot of satellite receivers on orbit. Right now, there just aren't enough of them to get the kind of data we'd like to be able to better forecast the weather. So as yet another application, if you had really cheap satellites, you could do much more of this and enhance weather forecasting and climate modeling. Another is real-time disaster response. These are two really amazing photos that both taken by Planet Labs, which a company you've all probably heard of. Right? It's sort of a CubeSat remote sensing startup in the Bay Area. These are two pictures they took over the last few years. The top left one is a picture taken in America in Wyoming, I think 2 summers ago. And the track you see here in the middle of the image is a tornado going through some fields. And this was taken in real time as the tornado was moving through these fields. And in this case, it was just pure luck that they got this image. The picture on the right is a picture of Kathmandu in Nepal just after the huge earthquake they had there a few years ago. So both of these, I think, illustrate the power of satellite imagery and remote sensing for disaster response. The problem with this is that currently what are called the revisit rate, the time between images that you can capture with a given satellite constellation, with current satellite capabilities, this revisit rate is anywhere from days to weeks. So you only get a picture of a given spot on the Earth every few days, maybe in the best case, and every few weeks in the worst case. And it's not enough to get this kind of real-time data. These are just lucky shots. But you can imagine you could bring that revisit rate down to hours or minutes by deploying more spacecraft. You could imagine getting pictures like this as events unfold on the ground and being able to see exactly where things are happening and exactly where to target response efforts to save lives. Another that I've personally been sort of very fascinated with for a long time and would like to do more, and we've been trying to sort of do something like this for the last several years with some collaborators now at University of Colorado Boulder, is wildlife tracking for sort of climate change and these kind of things. It turns out there are very interesting species that migrate, over large distances, over half the globe in many cases, across oceans, where the only way to possibly track them is from space, because they cover such huge distances and across national borders and oceans where you couldn't track them with terrestrial infrastructure. So there's been a couple of efforts and a lot of interest in doing this for many years, but it's a huge challenge. And there currently are not enough space assets to do this kind of tracking of these very small tags that you might like to track on wildlife to see how their migratory patterns are influenced by human interventions and climate change. And finally, as we're all kind of space people here, there's obviously lots of interesting things you might do in the realm of space exploration if you had lots of very small satellites. Here's just a couple that I've been involved in thinking about over the last few years. One in the top left is a sort of concept photo of this is a picture in the bottom right of Enceladus, one of the moons of Jupiter that has, or Saturn, sorry, that has liquid water ocean and these famous geysers of salt water that have been detected. And there's a lot of interest in going back to Enceladus to investigate these plumes from these geysers and to try to interrogate them to see if there are signs of life. Unfortunately, this is really difficult to do with a classical large spacecraft, where you only have one of these spacecraft and it's very exquisite and you don't want to crash it and this kind of thing. But if you had hundreds or thousands of these tiny low-cost satellites, you could imagine deploying them from a larger mothership and in very low orbits where you don't necessarily care if they crash into the surface, and they could each collect, many point measurements in different areas. So this is one idea. Another that I'm a big fan of, that a former lab mate of mine, who's now at Applied Physics Lab, has worked on in some depth, is exploring asteroids, potentially for resource extraction that we've heard of, perhaps mining asteroids. And the idea here is that to investigate an asteroid with a classical large spacecraft takes a huge mission, huge cost, and you need to capture around the asteroid and then orbit it and very slowly lower the orbit as you study it and try to estimate its gravitational field, which tells you about the internal composition and all this good stuff that you want to know. But doing this with a classical large spacecraft is extremely expensive and takes a long time. Another way you might go about this, that is measuring the gravitational field of an asteroid and then extracting information about its density and internal composition, would be possibly with a swarm or large number of very small low-cost satellites like these ChipSats, where in a sort of massive flyby where you don't have to capture, you don't require a delta V maneuver, you could look at the gravitational perturbation that the asteroid exerts on, say, hundreds or thousands of these chipsats in a one-shot flyby, and then extract a bunch of information about the gravitational field without having to do a capture maneuver and without having to have a large sort of exquisite mission. Okay, so these are some crazy ideas. I want to sort of seed the discussion with these and maybe prompt some thinking and discussion on your part to see what you guys can come up with. Now I'll switch gears and sort of tell you about some of the things we've done working towards some of these ideas. So the first is sort of this key idea of trying to reduce the size, mass, and cost of a spacecraft. This started out when I was actually an undergraduate student way back in about 2007 or 2008. I was an undergraduate student at Cornell working for Professor Mason Peck, who's done a lot of really interesting things. And this started as kind of a thought experiment on sort of how small could we possibly make a spacecraft. And the idea that originally came up was, could we make a spacecraft on a chip, which was kind of the origin of this ChipSat idea. And in fact, I did spend some time trying to make an actual chip, an actual sort of custom ASIC. And we kind of thought about making multi-chip modules, and I did a lot of depackaging of integrated circuits and wire bonding and stuff like this. And we quickly decided that that was going to be both very expensive, very time-consuming, and sort of maybe not worth it in the end. And instead, we sort of switched gears to trying to design what's really what we still end up calling a chipsat for descriptive reasons, but is in fact more like a printed circuit board satellite. And that's what you see here. And this became really viable at that point, thanks to a lot of advances in the consumer electronics industry around the same time. This was sort of right after when the first iPhones were released. So there was this huge availability of consumer devices like chip scale IMUs, microcontrollers, radios, all this kind of stuff. That this is also right around the time when the Arduino came out, and all this stuff got a lot easier to do and a lot cheaper and more available. So kind of the timing was right to sort of begin doing this. And so as a little kind of exercise, I set out, as an undergraduate to try to build one of these things and build the smallest possible device we could with low-cost, off-the-shelf components. So this is kind of the fruit of that effort. This was what we call the Sprite, and it's still, to my knowledge, the smallest spacecraft that's ever been built and flown. So what's on here? It's a printed circuit board. It's about 3.5 by 3.5 centimeters, weighs about 4 grams. There's a solar panel, and there's actually one on the other side as well. There's a microcontroller, which is kind of the little computer, the brains of this thing. There's a radio transceiver, a UHF radio transceiver. That's the sort of radio that are in all kinds of things these days, like car key fobs are actually where this one was, I think, originally marketed for, to open your car doors. But many, many other things that these are now in. Let's see, we have a MEMS gyroscope on here and a MEMS magnetometer that we're on here kind of for fun to see what kind of sensing we might be able to do. But we've since then put on all kinds of small single chip sensors, and finally an antenna. This antenna is actually made of nitinol, this so-called memory metal stuff, for reasons that you'll see in a minute. So this is kind of an early effort at building one of these devices. We got some interesting opportunities to fly these in the next couple of years. So this is our first chance at flying these. This was a mission called Missy 8. That was a material science experiment placed on the International Space Station on the outside of the ISS. It was actually launched on STS-134, which is the second to last space shuttle mission. And here's a few pictures of when this was installed. So this is a picture taken from the cupola on the ISS, sort of by an astronaut looking out the window. These are the two astronauts on the spacewalk installing this thing. If you look carefully, this astronaut's holding a camera and taking another photo. And then here's the second astronaut also holding a camera and taking another photo. And here's finally that last photo. This is a picture of a picture of a picture taken in space. And this is the full Missy 8 experiment here. This was an experiment to test sort of exotic materials, semiconductors, this kind of thing in the space environment. We got lucky and another experiment pulled out of this at the last moment. And my advisor, Mason, got a call offering us space on this experiment to fly something on very short notice. We kind of scrambled to put these together. So these are our little chipsats. These are earlier versions of them that were put together kind of in a couple days scrambling to get them on here. So they look a little different than the one I showed you before, but same basic idea, sort of epoxy down to this thing. And unfortunately, this whole thing was mounted on what's called the anti-nadir side of the space station. So that means Earth is down here to the lower left in this picture. And this whole experiment was actually looking out away from the Earth into space with a big hunk of space station in between Earth and our chipsats. So unfortunately, we couldn't get any signals from them, but we did get them back a couple of years later. So these things actually spent 3 full years on orbit. Here they are, and we got them back in the lab after spending 3 years on orbit. And sure enough, you can see they're a little worse for wear. It turned out that the epoxy encapsulant we had used darkened under UV exposure, which is not something we knew about ahead of time. So they got a little darkened, but they still worked. We put them under a sun lamp in the lab and they started transmitting right away. So this was kind of an interesting data point that showed that the sort of low-cost consumer-grade electronics we were using on these could, in fact, survive for long periods of time in low Earth orbit. So after this experiment, we decided we really wanted to fly these things as free-flying spacecraft in low Earth orbit. And around that time, we kind of hatched this idea of building a CubeSat that would act as a mothership for maybe 100 of our chipsats, and do something like in this video where we deployed a whole bunch of them in low Earth orbit from a CubeSat. So this was the concept. We called this idea Kicksat for 2 reasons. One is sort of evocative of kicking out a whole bunch of these tiny satellites from this mothership. And the second reason is that I, in an act of desperation as kind of a starving grad student, put this project up on Kickstarter to raise the money to actually build the spacecraft. So this is kind of a really interesting experience and one of the first crowdfunded space projects. So we raised about $75,000 over the course of a couple of months. And in exchange for the money, you might ask what people got for this. So we did a few things. At the lowest level, people got their name or a message engraved on the side of the sort of mothership satellite. And you can see a picture of a bunch of these here. So this was very fun. At the high end of the scale, we actually made a bunch of these little development kits so that people could make their own experiments to fly on an actual chipsat and really kind of have their own satellite. This was really cool, actually. So we had about 10 people go in at this development kit level. Most people didn't do super interesting things. They sort of, sent out little tweets with like, I heart so-and-so, this kind of thing. But a couple interesting things were done. My favorite one was an experiment that was hatched by some folks at the British Interplanetary Society who actually sponsored 2 of these things. And the idea was to use the SRAM on the microcontroller as a radiation detector by writing bits to it and then reading them back and sort of doing error checking over and over again to look for bit flips. I thought this was super clever. And I later found out this was not a totally original idea, although I think these guys in this had come up with it on their own. Turns out this was done actually back in the 90s on another mission that went to the moon and was successful. So this has some precedent. So you can turn your RAM, it turns out, into a radiation detector. So that was super clever. So switching gears then again to some of the more interesting, kind of in the weeds technical stuff that I had to figure out as a grad student to pull this off. One of the trickier ones for me, at least, coming from an aerospace background, was figuring out how to communicate with these things. So these are very tiny, obviously, very power constrained, no pointing capability, so low gain antennas. So how do we talk to these little chipsats when they're 1,000 kilometers away in space? So the other sort of thing to note here is that we wanted to do this with very low cost hardware so that amateurs and students could sort of go out in their backyard and listen to these satellites themselves. So here's the ground station gear we use for this: the handheld Yagi antenna, a laptop, and a USB dongle, basically, is what you need to talk to these things. And you might wonder how this is possible with only sort of very small antenna, very limited power on the spacecraft side. In fact, the transmit power on the radio is 10 milliwatts. So how do you close this communication link? And I'll kind of illustrate how hard this is with some visual stuff. So this is what the RF looks like coming out of the transmitter on the chipsat. And this is sort of phase shift keying. So you can see where the sine wave kind of flips. These are bit transitions. And if you know what you're looking at, you can kind of read the bits right off this as it comes out of the transmitter. Here's what it looks like when we receive it on the receive side after having traveled 1,000 kilometers. It's basically all noise, and you can't really see anything in here. In fact, if you look at this in the frequency domain, it just looks like white noise. It's totally buried. It's under the thermal noise floor. So how do we pull these signals out from under the thermal noise floor? The basic trick is one that's borrowed from GPS and consumer cell phones. And this goes by a bunch of names. In cell phone lingo, it's called CDMA, which you may have heard of. It stands for Code Division Multiple Access. And it's how you differentiate individual cell phone users when everyone's on the same frequency. And then the basic underlying math of how this works is something called a matched filter. So the idea is that you assign each chipsat a unique ID code, and these codes have to be specially chosen. We use a set of codes called gold codes that are the same ones used by GPS. They have to have certain mathematical properties, sort of like orthogonality properties. And the idea is you have this ID code that each chipsat is assigned. And instead of just transmitting sort of individual data bits, when a chipsat talks, it modulates its signal with this ID code. So it's transmitting this ID code sort of for every bit, and it kind of flips this around to transmit bits. What happens in the receiver now is the receiver knows the ID codes of all the chipsats, and it does something that's effectively a sliding dot product. So it basically looks for this ID code, sort of does template matching in the receiver. And if that ID code shows up in the incoming RF, there's a big spike that comes out of this sliding dot product thing called a matched filter. And it turns out you get an effective gain from this that's equal to the length of the code. So what this sort of lets us do is trade data rate for gain. So we can get away with a very low power transmitter, a very small, modest antenna. But basically, by sacrificing the data rate, effectively by transmitting this ID code every time I want to transmit a bit, and chopping the data rate down, effectively it lets us integrate up the energy in that whole code, the whole length of that code, and sum that up into a single bit. So we can, in fact, pull these signals out from under the noise. And on the Kicksat mission, we used codes that were about 500 bits long, which means we got a gain of about 500x, or about 27 dB, which is equivalent to having a really big dish, right? So this it makes up the gain. The data rate here, the net data rate after all the signal processing tricks, is about 100 bits per second net. So it's slow but not crazy, and you can send interesting information this way still. So that's kind of how we do it. This is a ground test we did when I was out at NASA Ames in California working on this stuff. It was actually my wife I convinced to drive up a mountain and hold this thing up for me. This is our very scientific official test rig of piece of cardboard with the chipsat taped down. And my wife was, told to go up there and hold this up facing the sun. I was about 50 kilometers away down in Silicon Valley over here at Ames. And we added attenuation on the receiver to mimic the sort of 1,000-kilometer distance that we'd see going to space. And this is the output of that matched filter when a bit comes in. So you can see this nice big spike, very visible above the noise floor. And so this whole thing kind of works. This is an on-orbit test we actually got to do a few years ago, where we basically piggybacked a chipsat on a German-made research satellite called Max Valier. So this is Max Valier. This is our chipsat on a little 3D printed mount attached to the side of it. Totally self-powered, totally independent of the sort of mothership host satellite here that we hitched a ride on. And these are the first chipsat signals successfully received from space by some friends at TU Delft who had a nice ground station and took a peek. So you can see these lines on this waterfall plot. These are the signals coming from that chipsat on Max Valier from a couple thousand kilometers away up in space. So this is our first demonstration that this all worked from orbit. So I would like to switch gears a little bit again to show you some of the kind of more researchy things we're doing these days to try to enable some of this stuff that my lab is currently working on. So building on this communication stuff, it turns out the sorts of signal processing tricks we played here with these ID codes, so-called PRN codes, and the match filtering, turns out these kind of tricks are also exactly what's used in radar to do ranging measurements. Turns out you can repurpose this stuff to do a pretty good job at ranging. So we've kind of also started to look at how we might be able to use some of those signal processing tricks to do relative navigation on small satellites generally, but in particular sort of swarms of what might be CubeSats or maybe slightly larger spacecraft, and how you might use this to do navigation in interesting places sort of outside of low Earth orbit where you don't have GPS. So let's think about this problem for a sec. Let's say we have 3 satellites like this, and they are doing ranging, between each other. This tells us some information about their relative positions, but there's an inherent ambiguity here, right? So let's say we have these range measurements between these 3 satellites. That tells me sort of this configuration maybe of this triangle, what the sides on the triangle are, but it doesn't tell me anything about the orientation of that triangle or absolute position of that triangle in space, right? I can kind of rotate this around and I would still get the same measurements. So we need some way of overcoming this ambiguity. So here's a few ideas you might do, right? One is you could have sort of another spacecraft, sort of mothership spacecraft that knows its absolute position, that can act as a reference that these can all talk to overcome the ambiguity. Another would be to use some kind of ground station asset on the ground that knows that they know where it is to overcome the ambiguity. But let's say we don't want to do these things, right? We want to do this in say at the moon or an asteroid where we don't have this kind of external reference, or we don't want to, or it's too expensive to talk back to Earth all the time. So another way we've thought about doing this that's related to the asteroid gravity idea is to in fact use the body you're orbiting, use knowledge of its gravitational field to overcome this ambiguity. So it turns out that the moon in particular has a very well-characterized gravity field. We have really high-resolution maps of the Earth's gravity field down to better than 5 kilometers, thanks to a mission called Grail from a few years ago. And it turns out the moon's gravity field is very irregular and lumpy. And these small sort of, the lumpiness of the gravity field induces small perturbations in the orbits of the satellites. You can imagine if you have 2 satellites, one following the other, and you go over an area where there's more mass and therefore stronger gravity, the first satellite will kind of get attracted more and speed up a little bit. So the range between the satellites will increase. And then a little while later, when the second satellite passes over the same mass concentration, it'll catch up. And so you get this time varying sort of perturbations in these range measurements. If you have a good gravity map and you have sensitive enough ranging, it turns out you can use that gravity map to back out the absolute positions of the spacecraft just using relative range measurements, which is kind of a cool thing. So we worked a bunch on this idea and recently flew a mission in collaboration with NASA Ames called VRex to test this out. These spacecraft are actually still in orbit now, and we were able to get some of this data. So stay tuned for those results. Hopefully in the next few months, we'll have some publications out on this. These were larger, obviously, CubeSats, but the same ideas apply to smaller things like the ChipSats we've worked on. In fact, we can do these range measurements. We use the same radios in these CubeSats as we would use on the ChipSats, so it transfers quite nicely. Some other interesting challenges associated with these very small spacecraft that we've been working on is actuation. So this is a fun plot of the total mass fraction that's consumed on a spacecraft by the actuators. So in this case, this is for the attitude control system, and these typically are things like reaction wheels or control moment gyroscopes. But the idea here is that, and this is a picture, by the way, of a CMG or control moment gyro that's used on the International Space Station. So International Space Station is huge, right? A couple of football fields in size, but the actuators on it, they're big, but they're like, less than 2 meters across, right? You can see here. And there's 4 of these on the ISS, and that's what the ISS uses to maneuver. So compared to the size of the ISS, this is relatively small. And if you look at it as a fraction of the overall mass of the spacecraft, it's only 0.2%. It turns out what happens, though, is as you go to smaller spacecraft, that fraction increases. So on something like a geo-communication satellite, this is a couple of percent. On sort of a low Earth orbit small sat, what traditionally would be considered a small sat, is something maybe the size of a large refrigerator that's maybe an Earth imaging spacecraft. It's up around 5 to 10%. And then we get down to CubeSats. So this is a 3U CubeSat, maybe something like what Planet Labs flies, something the size of like a shoebox, 3 kilograms or so. These actuators now take up a third or more of the overall spacecraft mass. So they start to take up a good chunk of the spacecraft. And as you go smaller and smaller, this trend is not good, right? So now if you think about at the chipsat scale, it's possibly not even viable to do this. Like how do you fit these kind of actuators on something that only weighs a few grams? So we've had to look at alternative actuation schemes and kind of getting away from mechanical actuators on these really small platforms. And one of the most promising ideas we come up with is to use magnetic torque coils. So this is not a new idea. Right? This has been used on spacecraft for decades for what's called momentum dumping, to desaturate or offload angular momentum from more traditional actuators like reaction wheels. The reason this isn't used, or has not been used historically for 3-degree freedom of attitude control, is that it's under actuated. So what that means is, so here's the basic equation that governs torque due to magnetic interactions. This is torque tau equals m, which is the magnetic moment generated on the spacecraft. So if we have a set of electromagnets or torque coils, like this one pictured here, we can make any m we want, basically. So this is a vector, and we can use a combination of coils to make this vector be whatever we want. That's our control input. And then B here is the Earth's magnetic field. This we can't pick, right? This is whatever it is, whatever the Earth's magnetic field is, where we happen to be at that instant. So what this says, though, is, okay, I can pick M, I can't pick B. There's a cross product here to generate this resulting torque. And as a result here, I can only generate a torque in the plane perpendicular to B, right? If you remember your right-hand rule, I can't generate any torque parallel to the B vector. So I only can ever produce instantaneously 2 degrees of freedom worth of torque. So this is a problem, and it makes this problem hard from a classical control perspective. But the interesting thing about this is that this B over here is not static, it's time varying. So if you look at this picture, right, this is kind of a cartoon picture of the Earth's magnetic field. It's like approximately a dipole, but it's actually kind of messy and way more complicated than that. And if you're in orbit around the Earth moving around, as you move around the Earth, the B changes. So if you're a little bit clever about things, if you have a map of the magnetic field, which we do, we have good maps of the magnetic field. And if you know where you are, if you have like a GPS receiver, you know your orbit, then you can know what this B is going to be ahead of time. You can predict it along your orbit. So knowing all that information, knowing where B is going to be as it moves around as you move in orbit, you can solve a planning problem that looks ahead the next, say, 5 minutes and forecasts what the B vector is going to do, and then uses that prediction to generate whatever torques you want over the next 5 minutes, say, to get your spacecraft pointed the way you want. So in fact, you can overcome this under actuation. It just requires being a little clever and having a map and knowing where you are. So we've actually implemented some algorithms to do exactly this. And here's a kind of a cartoon drawing, a sped up version of this. Again, shown on a CubeSat, but sort of the inspiration for this is very much chipsats. And this is sped up. This is actually occurring over 4 minutes. And you can see that this executes kind of a funny nodding motion instead of going directly from the initial state to the final state. And that's due to this time varying B field and taking advantage of that time varying magnetic field vector. It's kind of fun. So this works, and we're kind of currently looking at trying to do this on orbit on a future mission. So this is one way to go. The problem here, though, is this takes time, right? It takes, say, 4 or 5 minutes in general. And it's not super precise, right? It depends on good knowledge of the Earth's magnetic field, which is a little bit uncertain, and good knowledge of your position, all these other things. So we think we can make this work to within, say, 5 or 10 degrees, not super fine pointing. To get really fine pointing, we have some other ideas inspired by nature, actually. So turns out geckos are very good at attitude control. Let's see if we can get this to play. So geckos are actually able to right themselves and do full 3 degrees of freedom actuation with their tails, as you can see in this video. The interesting thing about this, these geckos weigh about 3 or 4 grams. They're actually about the same size mass as our chipsats. So this, I think, is a really good sort of bio-inspiration for how we might be able to do attitude control on things as small as chipsats. And maybe the idea is to put tails on our satellites. And just for fun, turns out this sort of thing, people can actually do this too. These are some experiments done in the 90s on the space shuttle mid-deck, showing people kind of wiggling around and using funny motions with your arms and legs. You can actually perform attitude maneuvers, like very, very much like the gecko tail thing. So maybe we need limbs, arms, tails on our spacecraft. So this is kind of a demonstration that we did with 3 boom kind of actuators, tails, arms, whatever you want to call them. This again is a CubeSat scale device, but same idea applies at very small size scales. The reason this works at smaller scales than, say, traditional reaction wheels is because of the way inertia scales. So inertia goes like ml squared, mass times length squared, right? And so with a reaction wheel, you have a little flywheel spinning inside your satellite. With these booms or arms or tails, we have this big long arm extending out from the spacecraft body, and the inertia of that thing goes like length squared. So by extending the boom out from the spacecraft body, we get a length squared advantage here in the inertia, which makes our actuator much, much more effective than some tiny little wheel that we would sort of have to pack inside the satellite. So for smaller spacecraft, this is a huge win. And this, in fact, also lets us do very fine pointing. So it sort of grew out of thinking about chipsats, but now we're actually looking at this as a means to do very high precision pointing for things like small space telescopes, potentially on CubeSats for doing things like exoplanet imaging. Okay, so finally, to wrap up the talk and switching back to the sort of hands-on chipsat stuff, this is Kicksat 2. This is back in 2018 at Stanford, and this is the full complete spacecraft. This is our deployment test, showing you what this thing actually looks like in action during some testing on the ground. So that's Kicksat, and we finally got to launch this thing, like I said, back in 2018. And I was fortunate enough to be able to go watch this launch at NASA Wallops. This is the Northrop Grumman NG-10 mission. And we rode up as a secondary payload on this Cygnus vehicle. It was an ISS resupply mission. And this video here is the last footage of Kicksat ever. So this is the deployer that the CubeSat's riding in, the sort of mothership spacecraft on that Cygnus vehicle. This is after it was after the vehicle went up to the ISS, docked, unloaded supplies. They filled it with garbage. It undocked from the ISS and did some maneuvers, and then they dropped us off in a lower orbit below the ISS for safety reasons. And you can see Kicksat get deployed right there. There it goes. And a few days after this, we sent a command up to the CubeSat, the mothership spacecraft, to command it to deploy all of the chipsats. And at that point, we went up to the sort of famous Stanford dish. This is up on a hill behind the university campus. This big dish, got to use the dish. And here are the signals from a whole bunch of chipsats coming down as recorded by the dish here. Right after they were deployed from Kicksat 2. So a couple of kind of interesting sort of closing thoughts here. This was a long saga. It took many, many years, all the way back, starting in, say, 2008, 2009 or so, when I was an undergraduate, all through my PhD, and finally getting to fly it when I was an assistant professor in 2018. So it took, better part of a decade to actually make this all happen. And a lot of help, a lot of interesting people were involved in this along the way in various ways. One of my favorite things that happened as part of this was during a couple of Kicksat missions we got a huge amount of interest and involvement from the broader community, from amateurs and people just generally interested in spaceflight, both through the Kickstarter effort and through the amateur radio community. And we actually ran a Google Groups forum for mission ops during Kicksat. We had amateur radio operators all over the world pulling down packets and kind of posting them in Google Docs and talking on Google Groups to coordinate things. In fact, we had a whole bunch of people who weren't amateur radio operators who just thought Kicksat was cool and wanted to get involved, come and join us here. And we had several people sort of parsing the packets and plotting things, plotting telemetry data in Google spreadsheets. We had one guy who was not an amateur radio operator, was interested in orbits generally and this kind of thing, run re-entry predictions for our spacecraft based on the latest TLE data from NORAD. And he actually did a better job of predicting when the spacecraft was going to re-enter than NORAD did, which is very cool. So we had this great, totally international community of amateurs, some people who'd never been involved in anything like this before, never, amateur radio, anything like this, and just thought this was cool and decided to help out and get involved online. And I really love this idea of just anyone who wants to, who's passionate about space, being able to sort of get involved in a tangible, real way in a spacecraft mission. I just think this is like one of the coolest things that that I wish I had when I was a kid. That sort of just makes me happy about this whole thing, and it gets me excited about this stuff. So yeah, this kind of democratization idea. And then along those lines, we've actually open sourced just about every aspect of this whole Kicksat thing. Some of these pieces have kind of taken on a life of their own and been sort of extended in various ways. And one of those is the avionics in the CubeSat mothership. We actually broke out and open sourced on their own as a separate thing that we call PyCubed. So this is an open source avionics stack for CubeSats. We call it PyCube because it runs Python. And these have been now flown on 3 different spacecraft missions. So they've been tested on orbit. They've actually been radiation tested. They've been through all kinds of qualification testing, and they have flight heritage. And so there's a lot of kind of lessons learned and careful design work that went into these. And they're easy to program. And we've also sort of used them in university capstones with undergraduate students several times now. So they cost about a couple $100 to make yourself if you want to. And we're actually gearing up to try to make a whole big batch of these at a PCB fab house to be able to sort of sell them and distribute them more broadly to amateurs and university capstone teams and this kind of thing to get more people involved. So it's as far as I can tell, I'm aware it's kind of the lowest cost, lowest barrier to entry way to get started with a CubeSat. And yeah, along those lines, you can find all of our stuff online on GitHub. There's kind of the mechanical designs for the CubeSat, the deployment mechanism for the chipsats, all the avionics for everything, all the flight software for everything, all online. So if you're curious about this and you want to dig in more, feel free to Google it, look it up on GitHub, and dive into all the technical stuff. And finally, just to wrap things up, as was alluded to, I'm involved in this project called Breakthrough Starshot, which is kind of maybe far off in the future idea of sending something like our chipsats to our next neighboring solar system, Alpha Centauri. And the basic idea is to take a very lightweight spacecraft, gram scale spacecraft like one of our chipsats, attach it to a big light sail, and shoot it with a big ground-based laser to accelerate it to something like 20% the speed of light so that it can travel to Alpha Centauri in about 20 years and potentially take pictures or sensor measurements of another planet around another star. So that's kind of it for me. I'd like to sort of also plug my fantastic PhD students who've been working on this project over the last several years in various ways. They're the ones who actually do all the hard work, and our various funding sources and collaborators who've supported Kicksat in its various incarnations over the last several years. And with that, I'd love to open it up, take questions from everybody. And if you'd like to get in touch with me or look at some of our work, this is where you can find us. It's my email, GitHub, and the lab website.
Great, fantastic. Yeah, thank you so much. Very exciting. First, we have a couple of questions on, but I don't know whether you can read it or not.
Yeah, let me try to. I can't read it with the presentation on, so let's see. But yeah, where is this?
It's from Eric Chu, who is my student, and he is interested in chipsets. In fact, And he showed me just a piece of paper, say telling me that it's a chipset, which I could not imagine. But okay, so what did he ask? He said what?
So yeah, some things about kind of classic GNC, sort of how do we do navigation, attitude determination, this kind of thing. So the chipsats that we've flown so far on Kicksat that I showed you, those do not have any form of attitude determination or control on them. I showed you some of the ideas we have for doing attitude control. The magnetorquer stuff is the closest stuff to actually working and flying. And we've actually done a lot of work on that magnetorquer-based control strategy. And in simulation, we've built prototypes. So that's actually basically just waiting for a ride. Like we can do that now. And the next time we get to fly something, we'll probably try that out in space. As far as attitude determination goes, right now, we're using kind of very low-cost, simple sensors. So we have a kind of classic setup where we use sun sensing with simple photodiodes and a magnetic field sensor, a magnetometer, and along with knowledge of where you are and a reasonable knowledge of the Earth's magnetic field, you can do coarse attitude determination with this. But again, it's very coarse, maybe like 5 to 10 degrees accuracy. So that's what we do now, and what we're kind of planning on doing in the near future for attitude determination and control. Mm-hmm. For position knowledge, so right now, so we've done a few different things in this. We have actually put GPS receivers on some of these things, although we haven't flown them. So we can put GPS receivers on these things. I mean, basically it's the same GPS chip that's in a smartphone. So there's some challenge in doing this. Mostly it's because of legal restrictions on GPS receivers. There's the so-called COCOM limits that basically limit commercially sold GPS receivers to only working below a certain altitude and speed. Nominally, originally, this law was meant to keep these things from getting onto missiles and things like this. But they're, so it's challenging to basically to buy these things with those limits removed. But it is certainly possible. So maybe sometime in the future, we'll be able to fly GPS on these. In the meantime, we essentially, the sort of working plan for anything we do in the near future would be to just uplink orbital elements to these things after they're deployed, and then sort of on board they would just propagate their state based on the current time, based on having their onboard clock. So that's I think kind of sums it up. I also showed you some kind of future crazier stuff that we're thinking about in terms of navigation, involving swarms and relative navigation using just range signals and maybe knowledge of a gravity field. So there's a whole bunch of kind of crazy ideas in there, but the basic stuff that's nearer term is low-cost sensors, sun sensor, magnetometer, and these kind of magnetic torque coil ideas. Okay, so I think there's a follow-up question here about can such small chipsats be tracked by NORAD? So officially, no. If you talk to the people who run these radars, they'll tell you that they're too small to be tracked. That's kind of the official line. But the true answer is much more subtle. So basically, they can be, but the details are fuzzy. So like, what really matters from a radar perspective is having some kind of scattering or reflecting element that's sort of on the same order or bigger than the wavelength of the RF that the radar is using. So it turns out on our chipsats, the dipole antennas we use for our radios are big enough to scatter radar. So they probably are visible with current radars, actually. And we've had some talks with not the NORAD folks, because they kind of aren't allowed to talk to us about this stuff, the technical details of how their radios or their radars work, but with a commercial radar startup called Leo Labs that operates several tracking radars around the world that they built themselves, and they operate them and sort of publish tracking data as a commercial service. And they've told us that they should, in fact, be able to track these things based on the size of our antenna and the wavelength of their radar. So yeah, the official word is no, but the sort of the actual situation is probably And if we wanted to make them visible to a particular radar, it would just mean adding some kind of metallic deployable thing like a dipole antenna that's the right length to scatter that particular radar band. So we can make them visible essentially. Conversely, if you really wanted to make them invisible, you probably could.
But whatever NORAD said, no means yes, right? That's the answer.
It's tricky, but yeah. So NORAD says no officially, but the Leo Labs guys say they probably can track them.
And would you be worried about the space debris problem? I mean, since we are going to deploy 10 million of them, you know?
Yeah. So the debris problem has kind of been haunting this project, you know, for forever, and it's been kind of the main reason it took so long to actually fly these things. It was kind of overcoming a lot of those concerns. So practically speaking, so yeah, there are certainly some debris concerns. The main concern is around tracking them and making sure they don't end up sort of invisible and lost and you don't know where they are and they're just kind of flying shrapnel or this kind of thing, right? So what we've done so far is only deployed them in really low orbits where they're basically guaranteed to re-enter within a few days. So on the Kicksat 2 mission where I showed you these videos where the video where the CubeSat was deployed, that was actually at about 300 kilometers. So it's 100 kilometers lower than the ISS. And from that orbit, these things re-enter within days. And in fact, the CubeSat only lasted about 20 days at that altitude. And the ChipSats maybe 2 to 4 days. They re-enter really fast. So this is basically how we've sort of alleviated those concerns so far. It does make it quite restrictive what we can do with them. So since we're only allowed to fly them in these very low orbits, but another place we've kind of looked at doing interesting things with ChipSats is in space exploration kind of use cases where we're piggybacking on missions to other planets, and in those contexts, it's also kind of the debris concern is not really an issue either. So yeah, that's kind of the debris story. Let's see. Okay, so the GLEE project at CU Boulder. Yes, I've kind of been talking to those guys over the last couple of years, and they're basing their stuff on sort of my work and a work from another former lab mate at Cornell who kind of did some more ChipSat stuff after I graduated. So yeah, it's sort of all in the family. We sort of talked to them, and they're kind of doing some newer things based on stuff we've done. And then there's another question here about FAA licenses for deploying. So turns out, no, FAA is not involved in our licenses. So the FAA is in charge. So the licensing situation for any spacecraft mission is very confusing and complicated. In the US, at least, which is kind of the only place I know, the FAA licenses launches. So if you build a rocket, if you're SpaceX or Rocket Lab or ULA, you have to get a license to launch your rocket from the FAA. And that's because the FAA does things to ensure that the national air traffic and airspace is sort of clear, and that they route air traffic around the launch site when the launch is going to happen and all this kind of stuff. So the FAA is heavily involved in the launch end of things. So our launch provider, certainly in our case, it was Northrop Grumman on that mission I showed you, they have to get an FAA license for the Cygnus rocket, and lots of planning goes into this, and temporary flight restrictions around the launch site and all this kind of stuff. So that's all FAA. It turns out the actual spacecraft operator does not get an FAA license. So in our case, we ride along on this thing. So we get licenses from a couple of different government entities, depending on the situation. So for a generic kind of commercial spacecraft, the primary licensing authority in the US is actually the FCC. They license communications frequencies, but it turns out they've sort of more or less subsumed the role of licensing spacecraft and are in charge of licensing, and they kind of like they practically de facto license things based on space debris concerns as well. And then there's also NOAA, who licenses satellite remote sensing things. So if you have a camera on your spacecraft, you have to go talk to NOAA. So we've had to do that. And then if in certain cases we've flown things with NASA, where things are actually a NASA mission, and in that case, there's another government entity involved called the NTIA. So there's various, it depends on all the details, but there's roughly 3 or 4 government agencies involved in any one spacecraft mission, and it gets complicated. So yeah, that's sort of a roughly the story there. So we don't have to go to the FAA, but we do have to go to the FCC and NOAA typically, and the NTIA in some cases.
Okay, any other questions from the audience? You could also, unmute yourself and ask the questions. So one thing is that, for, as you mentioned at the beginning, that the Earth observations are the major part of the business, then. But if you have a camera, so-called camera on a chipset, that must be very low resolution, isn't it? I mean, you won't be on the, say, we are hoping to get something like 2 meter, ground resolution, and they won't be able to reach that on the chipset.
Yeah. So I think, there's sort of, I think a key thing to get across about this is that, you're never really going to compete on a sort of capabilities with larger, classical spacecraft. And we're not trying to, I guess, is kind of the main thing, right? So like remote sensing, if you're doing remote sensing and you want to achieve high resolution, you need a big aperture, and there's just no way around this, right? It's basic physics, diffraction limit, et cetera. So we're never going to have large apertures on these things. So we're never going to compete with a bigger satellite. Same deal with trying to do communications, where you really, if you want to have a lot of bandwidth, you need a big antenna, you need a lot of power, so you need large solar arrays. Never going to compete there either, right? So I think what we're trying to do with these is kind of carve out new mission capabilities, new mission concepts that are enabled by, I think the really interesting stuff here is where you can have many spacecraft spread out over some region and all taking measurements simultaneously. Say sparse distributed aperture kind of stuff, or in situ sensing. And there's a number of really interesting applications like that, where having large, say 1,000 spacecraft spread out, all taking simultaneous measurements gets really interesting. So, I mean, you could imagine, if you really wanted to do imagery, say, you could imagine, this is a long way off, but there are various interesting machine learning related techniques for stitching together lots of low resolution images into composite, larger, higher resolution images. But there's other interesting things you can do with other sensor modalities. So there's a lot of interest in studying the upper atmosphere and the ionosphere like this, where you fundamentally need lots of data points, simultaneous data points spread out to sort of get an instantaneous snapshot of what's going on with space weather, for example. Other things like the asteroid, gravitational stuff that we talked about earlier on. There's applications where there's kind of strength in numbers, right? And that's the stuff where I think this gets interesting. Not so much, right, for classical remote sensing kind of ideas.
Yeah. Okay. One last question. If nobody else, nobody else wants to ask a question, that is, you must have thought about this. You must have very nice answer to that. What is the limitation of how small a satellite can be? Can it be
I don't
like this one, like a corn, or like one.
I don't think we've hit that limit. So what we've done so far was done on almost no budget with off-the-shelf electronics very cheaply by like me as a grad student or undergrad even, right? So like this was not using crazy fabrication processes or super high-tech semiconductor things. It was very cheap off-the-shelf stuff just put together in interesting ways. So we're definitely nowhere close to the fundamental limits on how small you can make this stuff. I'd say probably the 2 things that you can't get around that are going to pose real physical limitations. One is power. So if you're doing energy harvesting, you're presumably using solar cells to collect energy, and that's you just need area to collect enough power to do interesting things. And the other kind of aperture or antenna size thing. So if you want to have a radio and you want to transmit or receive on a certain wavelength, you need an antenna that's sort of comparable in size to the wavelength somehow. So those 2 things make it such that there is some limit to just doing very basic communication. where you need an antenna and you need to collect enough power to do interesting things. Yeah, aside from that, I think you can definitely go smaller than we've done. Why you would want to, or what the motivating reasons to do so are, not clear to me at this point. But yeah.
Okay, thank you so much, Zac. I mean, that's excellent. And when are going to have new results? I mean, because we welcome you to come back and give another talk.
Thanks. Yeah, fantastic. So yeah, we're actually not flying ChipSats much these days. You may have sort of guessed based on the more recent work involving a lot of CubeSat things,
right? Because
we aren't allowed to. These debris concerns have kind of put the brakes on a lot of this work in the last couple of years. So we'll see what happens. I'm hoping we can find some other opportunities to fly these in the near future. But in the meantime, we're kind of doing a lot of tech development on CubeSats that sort of perhaps can be transferred to ChipSats in the future. Okay, good.
Just want to remind the audience that in the afternoon today, Phil called there will be another talk by Professor Kaufmann from Jülich, Germany. And they will tell him about what is happening on his end about CubeSat. Once again, I want to thank Professor Manchester, for a very nice and detailed talk, and then we learned a lot from you. And I think that my student Eric Zhu would know what to do from now on. That since you have done everything without any budget, right? He should do better. Okay.
I don't recommend it. It's not the best.
Maybe I should send him to you to teach him how to do it. Okay. Have a nice evening and have a good time.
Thanks, everyone.
Yeah. Bye-bye.
Bye.